All right, let's jump right into this explainer and completely demystify the incredible problem-solution framework behind modern, hyper-realistic game graphics. You know, if you've played a high-end video game recently, you've probably stopped your character just to look at a mountain range or a really dense forest and wondered how it all looks so incredibly lifelike. Well, that level of realism requires an absolutely mind-bending amount of geometry. We're talking about scenes constructed from literally billions of individual polygons. But how does your computer actually process all of that visual data in a fraction of a second? Let's find out.
Let's start with a number, a massive one. We're looking at this staggering scale of the Zora demo, a famous tech showcase which contains 1.64 billion triangles of pure geometry. To put that into perspective, NVIDIA released this specific scene as part of their ray tracing showcase, and it's this highly detailed, sweeping environment streaming in real time. But here's the crazy part. 1.64 billion is just the base. When you factor in something called instancing, where identical objects get repeated across the environment, that number explodes to nearly 18.9 billion triangles. Which naturally brings us to the ultimate question. How on earth do modern computers process these massive files in real time without literally catching fire? I mean, we demand 60 or even 120 frames per second at 4K resolution. So how is it physically possible to push nearly 19 billion triangles through a graphics card multiple times a second? It's a genuine mystery when you look at the raw numbers. The answer? It lies in an absolute masterclass of hardware innovation, software optimization, and, of course, artificial intelligence. Here is our roadmap for today. 1. The billion triangle problem. 2. Calling the unseen geometry. 3. Turing mesh shaders explained. 4. The DLS5 AI magic. And 5. The developer's heavy lift.
Section 1. The billion triangle problem. Staggering scale and memory limits.
What's truly fascinating here is that simply importing this 36.1 gigabyte raw geometry file crashes robust software in under 5 minutes. And that's even on top-tier machines armed with 192 gigabytes of RAM. Think about that for a second. That massive file size doesn't even contain the texture or shading data for most of the scene. It's purely the structural geometry. Just trying to open this raw data in Unreal Engine completely exhausts the system memory and totally crashes top-tier development rigs. It absolutely proves that brute forcing this amount of data is a complete non-starter. We need way smarter rendering pipelines just to open the files, let alone play them as a game.
Moving on to Section 2. Culling the unseen geometry. Discarding the unnecessary. Okay, so think of occlusion culling exactly like a Hollywood movie set, where only the visible fronts of the buildings actually exist. The graphics pipeline is constantly asking itself, is this object blocked by something else? By using hardware-accelerated occlusion queries, modern graphics cards can really quickly test the bounding boxes of objects. If the box is fully hidden by a wall, a mountain, or even another character standing right in front of you, the system just immediately drops it. This prevents the GPU from wasting its precious processing power drawing things that will never even reach your screen. You can see this logic in action perfectly with this car. With the roof off, the seats, the steering wheel, and the dashboard are completely visible, so they're being rendered. But the second that red roof is placed on top, the occlusion culling algorithm instantly realizes the interior is blocked from the camera's view. It just entirely skips rendering the inside of the car, which saves a huge amount of processing power. Now imagine applying this exact same logic not just to a single car, but to entire city blocks or mountain ranges and dense forests in an open-world game. It's a real game changer.
Section 3. Turing mesh shaders explained. Optimizing the scene.
Now, notice how the traditional vertex and tessellation pipeline is super rigid and honestly incredibly wasteful. The old way forced the hardware to rescan index buffers constantly, fetching data for back faces or hidden subpixels over and over again. The new Turing mesh shader approach, though, it behaves much more like compute shaders. They use a cooperative thread model, basically a highly coordinated team of workers building geometry directly on the GPU chip all at the same time. This means the memory is read exactly once, and the heavy lifting scales massively across the graphics card's shader units without hitting those terrible bottlenecks.
We can think of these meshlets as pre-packaged puzzle pieces that developers create to flawlessly fit into the hardware's really strict memory allocations. Instead of feeding the GPU an entire mountain all at once, you feed it these highly optimized, bite-sized chunks. And the specific numbers here matter a lot. By capping a meshlet at exactly 64 vertices and 126 primitives, it absolutely maximizes vertex reuse and fits like a glove into a 384-byte hardware block. This level of precision dramatically lowers the memory bandwidth requirements, which, has traditionally been a huge bottleneck in rendering. So the crucial takeaway here is that task shaders act as the ultimate gatekeeper. They efficiently reject hidden meshlets up front to just supercharge the throughput. Sitting right in front of the mesh shader in the pipeline, the task shader evaluates groups of primitives. If it determines a meshlet is off-screen or totally occluded, it just tells the mesh shader, hey, don't bother. It skips allocating memory for it entirely. First-generation hardware can actually spawn up to 64,000 child processes or branches per task, making this an insanely fast and scalable way to filter reality before it even gets drawn.
Section 4. The DLSS5 AI Magic, Smoothing the Transitions.
So how does it all look so smooth? DLSS5 acts almost like an AI video editor, filling in the visual blanks so you don't see ugly, popping artifacts when level of detail models transition. You know that feeling when you walk closer to a mountain and the game engine naturally swaps in a higher detail meshlet? In older games, this caused a really harsh pop-in effect that just completely ruined immersion. Well, DLSS5 uses deep neural networks trained on super high-resolution images to manage this. By utilizing temporal accumulation and motion vectors, essentially tracking how pixels move and change over time, the AI actually anticipates these geometric swaps. It smooths the transition flawlessly, giving you the cinematic realism without the crazy computational cost of brute force rendering.
But as you might guess, this AI magic comes with a hefty physical hardware toll. To calculate those perfectly smooth transitions, DLSS5 demands next-generation RTX 50 series architecture utilizing 4th-generation RT cores. It also requires a vast amount of ultra-fast memory. We're talking at least 12 gigabytes of VRAM and 32 gigabytes of system RAM just to hold the sheer volume of data buffers while the AI computes the frame interpolation. Visual perfection requires a truly massive engine under the hood, and the hardware requirements here are frankly staggering. Finally, Section 5, the developer's heavy lift. Behind-the-scenes preparation. We really have to acknowledge the monumental software preparation that developers execute before this rendering magic can ever hit your screen. Devs must run a rigorous, multi-step pipeline to break massive meshes down into the specific hierarchical structures that modern engines require. They can't just drop a 36 gigabyte file into a game and hit play. They use specialized tools to slice the geometry into tiny clusters, group them, and simplify them over and over again to create different levels of detail. This whole process is what prevents those annoying cracks from appearing between different clusters when the game dynamically scales resolution based on where you're looking.
And the time it takes is wild. When a developer first attempts to process these billion triangle files, it can take close to 10 minutes, literally leaving CPU threads completely idle while they just wait on massive individual objects to load. But by cleverly sorting the meshes so the largest ones process first, a technique known as external parallelism, developers can perfectly balance the CPU threads. This simple but brilliant move drops that processing time from over 9 minutes to under 3 minutes. It is a true testament to how crucial software ingenuity is to actually unleashing raw hardware performance. So what does this all mean for the future? As we wrap up this explainer, I leave you to imagine the next leap in visual fidelity as hardware, AI, and developer ingenuity continue to intertwine. I mean, we've gone from flat, chunky polygons to billion triangle micromeshes managed by AI on the fly in just a few short years. If neural networks are already hallucinating smooth transitions to save GPU power, how long until the AI is just generating the geometry itself in real time? That's definitely something to think about the next time you boot up your favorite game. Thanks for joining us for this explainer today.